So this is the third video for final exam review, a little tutorial if you wish, for chapters 7 and 9 for Physics 11. And chapter 7 was relativity, so a few things that we saw in relativity. On the upper right-hand corner here, got a really quick diagram of the Michelson-Morley experiment, kind of the very lead-in we looked at for special relativity. On the first day, we did talk about the two assumptions of relativity. One of them is that there's no reference frame that's preferred. So I'm just going to write that in here, no preferred reference frame. Now, some people like to actually phrase that another way. Putting this down here very, very cryptically, there's really no way to know who's stopped and who's moving. So if somebody asks you, hey, are you stopped? You never really know. So when people say, oh yeah, you can't tell if you're stopped or moving, that's another way to say there's no preferred reference frame. And the other one is the speed of light being constant, at least the speed of light in a vacuum, in every single reference frame. So I'm just going to write that in here. Speed of light, running out of room, why don't we just say constant? And I'm just going to add in there in all frames. Maybe we can actually get this right, in all reference frames. Okay, so those are the two things that you need to know to get into special relativity, and then it gets really interesting from there. So in a nutshell, here are the basic ideas that we talked about. Not all the equations yet, we'll do that over the next few pages. But the ideas in a nutshell are this. Let's say you've got a particle accelerator where there's some sort of gun here that's going to launch some particles towards a target. You could look at it from the point of view of that particle that's flying along. So maybe I'll put a little scientist on board here, and they're kind of watching this particle travel that distance from the gun, the particle launcher, the particle accelerator, out to the target. And it's going to take some time, and that single person, they're going to tell you that the time it takes is small, smaller than what the two people that we're going to put down below will say. They're going to tell you that the distance it has to go is all contracted and it's small. And they're going to tell you that the mass of that particle is also small. Now, if you compare that to maybe the point of view of a couple of experimenters who are down here, and they're actually watching that particle go flying by, and they watch it cover the distance from one little red stick figure to the next red stick figure, they're going to tell you that, oh, no, it's actually a really big time to go from the particle accelerator out to the target, and that it actually goes a really big distance. And that the mass, because it's moving by them, the mass is actually really big. And the difference between those two reference frames, if you're trying to figure out, well, how do you calibrate between the two? The little calibration factor is gamma. We can use that to go back and forth between the small and the big numbers. Now, a couple of things we saw. We looked at how if you had a spaceship zooming through space and then it shot some sort of cannonball off the spaceship with some velocity. Let's throw some other numbers in here. Let's say that the spaceship is moving with speed v1 and then the cannonball leaves the spaceship at speed v2. We found that the total velocity, it's not like what we learned at the very, very beginning of the course. It's actually not equal to v1 plus v2. We have to modify that, but Einstein has a way to do that. And the last thing we saw was that if you're willing to sever your emotional attachments to it, you can convert mass into energy. It's a little complicated. Maybe not all the mass will go, but certainly some of the mass is going to disappear. And that's one I'm going to throw the equation down for. That's good old E equals mc squared. And that's the kind of the guts of what we were doing with special relativity. And now down here at the bottom of the page, just a quick little review of the stuff that we saw, just a real basic idea of the theory for electricity. We looked at a couple of different types of circuits. We did look at series circuits. And for a series circuit, that's when all the resistors are in a line. And you're going to find that in that particular case, the current is definitely going to be the same for both of them. I'm going to put a little ammeter in here. And that current would be identical for both the 8 ohm resistor and the 12 ohm resistor. If I wanted to start measuring voltage drops, I could put a voltmeter in. It's got its little probes that reach around and test the voltage before and after something, and it reports back on the difference in voltage. And that's kind of, in a nutshell, what a series circuit looks like, guaranteed that the current's going to be the same in both of those. Maybe worth a quick little note here. So the resistors here, they have the same current. Now in contrast, down below we've got a parallel circuit. And for a parallel circuit, it's actually the voltage that's the same voltage drop. And you could go and drop in a little ammeter if you want in order to measure how much current's going into that 12 ohm resistor. If you wanted to see what the voltage drop is for that, you could take a voltmeter. You could actually connect it up before and after and see how many volts you're actually dropping trying to get through the 12. Both of these circuits have kind of a different plan for how you would go about trying to find the total resistance. Back up for the series one, the total resistance would just be resistance 1 plus resistance 2. But for the parallel story, it's a bit different. It's all about reciprocals, because you're actually looking at something called conductance. So 1 over the answer is equal to 1 over resistance 1 plus 1 over resistance 2. Now, some tools that we were using whenever we were trying to solve these circuits. We've got a couple of Kirchhoff circuit laws. One of them is for currents. This one's actually the easiest to see. In this picture here, I know the current in has to equal the current out. So if I notice that 7 amps goes into that junction and I see 3 amps go this way, there's really no doubt in my mind. This junction here tells me that that branch has got 4 amps on it. And another one from Kirchhoff is voltage loop law. Says by the time you go all the way around a loop, you have to spend all your money. So if we start here and we start off with 10 volts, or like we called it like $10 if you go shopping, if you spend $4 here, you've got $6 more that you have to spend. So this is a 6 volt drop trying to get through that resistor over there. Some other little techniques we've got. It's really just one, but we kind of looked at it a few different ways. We've got Ohm's law, which says the current is equal to the voltage that you apply divided by the resistance. And we found that we could actually use that one lots of different ways. You could maybe be sitting on one resistor and say, hey, how much current flows through resistor number 3? Well, that's voltage that you drop on number 3 divided by the resistance of number 3. You could also do the entire circuit. You could say, what's the total current coming out of the battery? Well, it's the total voltage that you've got at your battery divided by the total resistance of everything. And kind of a rare one that we used a couple of times whenever you got stuck, you could actually say, well, the current in a group, maybe a little grouping of resistors, it's equal to the voltage dropped across the group divided by the resistance of the group. We actually, to be honest, use that one most of the time if we had to try to find the voltage drop across the group. We usually knew the current and we knew the resistance of the group and we were trying to find the voltage of the group. When you want to go to try to find the power in a resistor, we've got some options here. The classic way to do it would be to say, okay, that's going to be the current multiplied by the voltage. But make sure you're grabbing numbers specific to the resistor that you're looking at. So for example, if you're trying to find the power that's actually being dropped or being dissipated at, let's say resistor 3, you'd want to know the current in number 3 multiplied by the voltage dropped on number 3. Maybe not the total current, depends if there's branches or not. A couple of other variants, we saw that you could go I squared R, but again, that would have to be the current in 3 squared and the resistance of 3 squared. And another option was V squared divided by R, but it would have to be the voltage dropped on 3 squared, maybe not the total voltage, divided by the resistance of 3. And that's basically the theory for the 2 chapters. And then in the next few pages, we'll try out some characteristic questions. Okay, so this first question here is a relativity question. We'll come back to the story about shooting a particle out of a little particle launcher towards a target. And according to the story, this particle is being launched pretty quick at 1.8 times 10 to the 8 meters per second. One of the things I would do right away is I would take that velocity and say, okay, great. Thanks for telling me the velocity, 1.8 times 10 to the 8 meters per second. That's great. Let's go and find the beta and then the gamma. So the beta value was just your fraction of the speed of light, just v divided by c. So you could take your 1.8 times 10 to the 8 and divide by 3 times 10 to the 8. We want to find out what fraction of the speed of light you're going. And in this particular case, the beta value ends up being 0.6. So you're going 60% the speed of light. Now you're halfway to finding this gamma number. The gamma number is going to be the stretching shrinking factor. And yeah, it's on the formula sheet here. It's 1 on top of the square root of 1 minus the beta number squared. So I'm going to go 1 minus 0.6 squared. And it's going to be a number a little larger than 1 when we're done. And this particular one happens to be a nice one. It's 1.25, right on the nose. That's the number I can use to stretch and shrink this story around. So I have these two different reference frames. One reference frame has the two people down below, and the other reference frame would be like a single scientist on board this particle kind of flying along at 1.8 meters per second from the particle launcher all the way over to the target. And so I've got a little bit of numbering going on here. I do know the time according to this single clock person, so that's a single time. It's going to be the lower of the two, and then I've got the mass according to that person, and I've got the distance it's going to go according to the two people down below. So if I was doing this question and somebody said, well, look, we want to know what this time is for the two experimenters down below in this red reference frame, well, they're going to have bigger numbers down here, right? So all of these are all going to be big. They're going to have a big distance, a big time, and they're going to see that mass going by them, so they're going to say that it's a big mass. So for their time, you're going to have to take the other time and make it bigger. We got to go 1.6 times 10 to the negative 7. And we're going to have to take that and stretch it. We're going to have to multiply by 1.25. We're going to multiply by that gamma. And that ends up being a time of 2.0 times 10 to the negative 7 seconds. And so I can just take that now and put that in here and say, okay, you guys, down in that red reference frame, you're going to get a bigger time, 2.0 times 10 to the negative 7 seconds. The 2 clock reference frame, right, so they got some clocks here trying to time this. The 2 clock reference frame's always going to give you a bigger answer for time than the 1 clock reference frame, this experimenter there holding a single clock. So yep, got to multiply by gamma to get that to work. Okay, so far so good. What I don't know yet is what this distance would be according to this single clock blue reference frame. They're going to tell me that it's a short distance, so I would have to take the 36 meters that the red experimenters would tell you, and I have to scale that down by a factor of gamma. I got to divide by 1.25. So they're actually going to say, or this blue person's going to say 28.8 meters, a shorter distance. And they've got a shorter time to get there, right? So far everything seems to be kind of lining up nice. Now, the 3 kilograms that we've got, that would be according to this person here. So they're on board. They're going to measure what we call a rest mass. They're going with it. So in their reference frame, that blue object is not actually moving compared to them. But according to the red people, it's definitely moving. So they're going to come up with a bigger value. And I can find out what that value is by doing nothing more than taking that smaller mass, that 3 kilograms, and just making it bigger by a 1.25, because this red story down here is going to have bigger numbers. And so they would say, oh, no, this thing's going by us. It's got lots of mass. It's 3.75 kilograms. And that's probably worth just a quick little note. Add right to this here. Masses are bigger when they're moving by you. Okay, next question. Got one of these addition of velocity deals where there's this spaceship. It's going past the Earth at 2.4 times 10 to the 8 meters per second, or what other people might call 0.8 c, and it's going to fire a projectile forwards really fast at half the speed of light, 1.5 times 10 to the 8. Now we're going to try to figure out what the addition of those two velocities would be. And you can do this 2 different ways. Either way is fine. Some people like working with the meters per second. So the equation, it looked like this. You had to add the 2 velocities, which I've already told you doesn't work, but you start with this. That's the top of a fraction, but then here comes the correction factor. Down on the bottom there's a big 1 plus, and then be careful, this is now the product of the velocities. 2.4 times 10 to the 8 multiplied by 1.5 times 10 to the 8. And all of that gets divided by the speed of light squared. So you got to do your order of operations carefully here. Down on the bottom, got to do all that multiplying and dividing first, then add the 1. And you can use that number now that's in the bottom to divide into that top value to come up with the correct answer. And in this case, if you wanted to practice this, you should come up with an answer around 2.79. It's less than the speed of light, times 10 to the 8 meters per second. Now, another option. A lot of people like this instead. They say, why don't we just use beta c values? Total velocity, we can add the velocities up. So we're going to have 0.8 c plus 0.5 c. That's another way of just talking about adding the two velocities. Then I divide by a big huge 1 plus, now here comes the product, 0.8 c and a 0.5 c all over. Now I'm supposed to put the speed of light in squared, but if you're going to play with beta c values, just go c squared. And then some really nice canceling happens. These two c's up here cancel with that c squared. And in the bottom, you just have 1 plus 0.8 times 0.5. No more c's down there. There are still c's in the top. So if you're cleaning this up, you're going to have a 1.3 c in the top divided by, down in the bottom, just a straight 1.4, no c's. And then that total velocity, it ends up being 0.929 c, which is exactly the same thing as this 2.78 times 10 to the 8 number. They're identical. So you can do that question either way. It's totally fine. Little nuclear reactor question. It says the mass of fuel in the core drops from 1,285 kilograms down to 1,273. So what you'd want to do is figure out, well, how much mass are you actually missing? So we can kind of subtract those here. So 1285 minus 1273. Okay, it looks like we're actually going to see 12 kilograms of fuel disappear. Okay, it gets converted into energy. So not all of the fuel is getting converted, but a portion of it is. 12 kilograms is. And now we can go and do our good old E equals mc squared. So we're going to take that mass that disappears, the 12 in this story, and then we multiply it by the speed of light, but you've got to square it. So you get an enormous answer when you're done. If I'm not mistaken, I think this is 1.08 times 10 to the 18 joules of energy. So it's quite a bit of energy. Okay, for number 4, we're moving into electricity. And it says we've got a 25 ohm resistor and a 55 ohm resistor, and they're connected in series. That's one after another with a 24 volt battery. And part A just says, all right, can you go and draw this? Can you draw a series circuit? Sure, we can do that. We just want to make sure we draw these things one after another. So I'm going to put my battery in here. The big end of that is positive. And then from my battery, I'm going to go off and do a series circuit. So I've got my first resistor. Maybe this is my 25 ohms. And then keep on going. I've got another one here. This one is 55 ohms. Just one after another. And then we'll go around a corner and we'll go back to the battery. Great. So I've drawn this circuit. So far, so good. And the current's going to come out of that positive end of the battery and head towards the negative. And the next question is, can you find the total resistance and the total current flowing in the circuit? Sure, yeah, we can do those. Those are actually pretty easy. So as far as total current goes, they're in series. So we can just add them up. We've got a 25 and a 55. All right, we're looking at 80 ohms in total. Well, we're here talking about the total current now. I'm going to go with all my voltage divided by all my resistance. So 24 divided by an 80. We're looking at 0.3, but don't stop there. Make sure you get 2 or 3 sig figs, so 0.30 amps. Okay, so far so good. Got that current now for the current leaving the battery at 0.3 amps, or if you want, you can call it 300 milliamps. I'm just going to kind of draw this in. That current comes out of the positive end of the battery, goes like this, goes through these resistors, and goes like that. goes from the positive end of the battery to the negative, and it's 0.3 amps big. Goes right on through both of those resistors. They both get that value. If you wanted to monitor how much current there was in that circuit, you could go and install an ammeter. You put it right on top of that wire. You'd break the wire open, sneak an ammeter in there. And they've asked us in 4C there to find the current and the voltage for each of those resistors. Well, they're both going to have the 0.3 amps. As far as voltage goes, you'd be wanting to take a voltmeter and extend it around each of those resistors so you can go and measure how many volts we're going to lose. In the end, we're going to lose 24 by the time everything is done, because this was a 24 volt battery back over here. But it's going to have to add up like a shopping trip to 24. So I'm not too sure what each of them is just yet, but I think we can figure that out. I do know that each one of those resistors is going to get that current of 0.3 amps. So let's go and see if we can figure out what happens at each one. In resistor number 1, again, it's on that wire. It's a series circuit, so it's going to have 0.3 amps. I know that I1 is equal to V1 divided by R1. So 0.3 is equal to V1 divided by 25. All right, that first voltmeter number 1, is going to be reading 7.5 volts. That's the answer I'd go with for that. For resistor number 2, it's on that main wire. It's a series circuit, so it's going to be 0.3 amps. I'm going to go to Ohm's law and say, you know what, current number 2 is equal to voltage drop 2 divided by resistance 2. So 0.3 is equal to the amount of voltage we're going to drop there divided by the 55. Not really surprised here at all. I knew it was going to add up to 24, and sure enough, the math cooperates. And it says, yeah, this one's going to drop 16.5 volts. Okay, great. Got that circuit totally taken care of. Both the currents are the same. The voltage drops are different though. We're going to spend more of our voltage on that tougher one to get through, on that 55 ohm resistor. All right, let's see what we've got going on here with the rest of these. So number 5, what's the power dissipated in the 55 ohm resistor? Okay, you've got choice there, right? We're trying to find power number 2. You could go current 2, voltage 2, or you could go current 2 squared times resistance 2, or you could do voltage drop 2 squared divided by resistance 2. But make sure you use values for resistor number 2. So I'm going to show you all of these just so you can see what the options are. If you wanted to do IV, you could go with 0.3 for the I and a voltage drop of 16.5. Or if you'd rather do the I squared R, fine. You could go 0.3 squared multiplied by 55. Or if you wanted to do the voltage, don't put in 24. You want to put in the voltage on just this one. You want to go 16.5 squared on top of the 55. Any one of those three is going to give you the right answer. Power on number 2 is 4.95 watts. So make sure you're grabbing numbers specific to the resistor that you're being asked about. Last one for this page. How much energy does the 55 ohm resistor dissipate in 4 minutes? Okay, well, for one thing, this 4 minutes, no thank you. We're going to have to change that to 240 seconds. Yeah, it's definitely something that's got to happen. Now, diving into the math, we know that power is measured in watts, and it's energy divided by time. We've already got that watts, 4.95, right? And we're now being told the time, so I'm just going to start subbing in some values here. 4.95 watts, 4.95 joules per second. Worried about how many joules overall? 240 is the time we're going to go for. It's just plug and play from here, and you end up with an answer that's 1188. But be careful, that's too rich on sig figs. So you have to trim that down a little bit. You can write it this way. You can say 1190, that's fine. And then the units for energy would be joules. So that's that one there. That was a series circuit where the currents are definitely the same, but the voltages are different. Now, over the page, we're going to take a look at something that's connected up in parallel. So it's kind of the reverse of what we were just doing with the one that was in series. So this first one says, or the first information says a 25 ohm and a 75 ohm resistor are connected up in parallel, 50 volt battery. Got to draw the circuit. Sure, here we go. Got my battery, big N's positive, and it's a 50 volt battery. And we're hooked up in parallel. So at some point, things split. Maybe like this. And we've got one resistor here, another one here. Then it's going to get back together and make its way back to the battery. So we've got a 25 ohm resistance side by side with a 75 ohm resistance. Okay, circuit's all drawn. Part B, can you find the total resistance and then the total current of the circuit? Sure, but be careful. Total resistance for things that are in parallel, it's a little more creative. It looks like this. The reciprocal of the answer is 1 over 25 plus 1 over 75. So you've got to flip those numbers around with your calculator, then add them up, and then flip them back. And when I tried that out, I found that this total was 18.75. It's always lower than the lowest of the ones that you're adding together this way. And now I can go and find the total current coming out of the battery. Now it is going to split at this junction right here, but coming out of the battery, it's going to be that total voltage divided by the total resistance. So 50 divided by 18.75. So we're looking at 2.67 amps. Going to trim that down to 3 sig figs. Now be careful. That's the current on this main wire all along here. You've got 2.67 amps. But then it splits. And I'm not too sure right now how much current goes down each one of those branches there. If I wanted to know with meters, I could go and take an ammeter, break the circuit open here and sneak an ammeter in. That would let me see how much flow goes on the 75 ohms. If I wanted to measure voltages, I could grab a voltmeter and I could go and connect it up like that before and after. But we're going to do it mathematically because the question says, can you go and figure out exactly how much current goes through and the voltage drop across each one of those resistors? Yeah, we can do that. That's actually not too bad to do. What I know is that the voltage drop on the two of them is going to be the same. And from just doing a nice little loop, if I start here, I'm going to gain 50 volts, and then I'm going to spend 50 volts on each one. So when I go to look at that first resistor, it looks to me like the voltage drop there is 50 volts. And when we go over and do the other resistor, voltage drop number 2 is also going to be 50 volts. Okay, here goes. The current through resistor number 1, it'll be the voltage drop across resistance number 1 divided by the resistance of number 1. So I've got 50 volts, and I'm going to divide that by 25 ohms. Okay, so 50 divided by 25, that's going to be 2. But I don't want to just say 2. I want to say 2.0. At least get a couple sig figs in there. That many amps. So just going down this one branch here, heading this way, 2 amps. The rest of it's got to go that way. We're going to see the rest of that 2.67 head that way. And sure enough, that's what the math says. Current number 2, I'm going to go with that voltage for number 2 divided by the resistance of number 2. So 50 divided by 75. Yeah, it's going to be 0.67 amps. That's how much goes the other way. Beautifully adding up. Okay, I'm just going to write this in here, 0.67 amps. Beautifully adding up to that 2.67 amps. So for the parallel story, the voltages are the same, but the currents are different. And then we've got just a little follow-up down here at the bottom. Power dissipated by the 75. Yeah, okay, we can do that. Let's just kind of summarize numbers for just that 75 ohm resistor. Okay, just that second resistor right here. For this one, the resistance is 75, the voltage is 50, and the current is that 0.67. Okay, so I'm just going to write this in, just what I've got so far. Resistance for number 2, 75 ohms. the voltage for number 2, 50 volts, and the current on number 2, 0.67. It's kind of rounding a little bit, but it's that value. So find some version of power that you're happy with. Remember, we've got lots of options, right? You could say, okay, power, it's just IV, or you could go I squared R, or you could go V squared over R. They're all good, but make sure you grab those blue numbers whenever you try any of those out. So if I'm doing this, I might go, yeah, okay, this power is going to be, let's just go IV. So 0.67 multiplied by 50. So we're looking at 33.3 watts. There's 2 or 3 sig figs, so things are great. How long would it take the 25 ohm resistor in order to actually dissipate 1,800 joules of energy? Okay, well, we're switching it around here a little bit. I notice that we're going for the 25 ohm resistor now and not the 75 ohm resistor. So we're going to have to go and take a look at what's going on with the 25. So for that one, the resistance, that's number 1, its resistance is 25 ohms. Voltage is 50, and the current on that one, sorry, this should have been voltage on number 1. They're the same anyways, but it should have been voltage on 1. And the current here is 2 amps. All right, so we're going to have to do a quick little calculation here and find out exactly how much power we've got for this one, because I don't know it yet. So I'm going to go power is equal to IV. So I've got 2 amps and 50 volts. Okay, so this is 100 watts. All right, great. And now they want to know how long would it take to actually dissipate 1,800 joules of energy. Well, you know, some people can probably just see it right now if you think about what watts actually mean. Joules every second. So you've got 100 watts, it's 100 joules every second, and we need to wait until we get 1,800 joules. I think it's going to end up being 18 seconds, but let's just see what happens here. So energy would be power multiplied by time. We're waiting until we get to 1,800. The power is 100, and we're looking for the time. Yep, it's looking like 18 seconds. So that one's all wrapped up. A couple things there when you're calculating power. Make sure you're grabbing numbers specific to that particular resistor. Might not be the total current or might not be the total voltage. You have to kind of look and identify what the individual numbers are. And for a parallel circuit, the voltages are the same, but the currents are different. Now when you're drawing in voltmeters and ammeters, voltmeters reach around before and after items, and ammeters just get installed in series right in place. You break the wire and you sneak the meter in. And that wraps up all the tutorials. Definitely come on in and ask for some help if you're not sure about anything, and use this as a guide for some things that you might want to refine a little bit. So you can go back through your notes and you can try out that exam review package that we've handed out as well.